Hello, my name is John Tayag, and this is my Ca2 of data science. My model is predicting the Metacritic score of video games. I sourced it from Kaggle.com with 12,000 rows and over 20 columns. Now, the columns I've used is release date, recommendation count, initial price, or is it early access, or does it have free to play? Who benefits from this analysis? The people that benefit is like the manager of Nintendo, where they need to report to the CEO on this performance of their games. Well, if they have all the data, like the recommendation count, does it have early access, does it have free to play, they can use this model to predict the Metacritic score and report to the CEO. Other people are like the CEO of Riot Games. They want to release a new video game into the market, but they're unsure if it will be a success. This model shows if low price games are highly rated, or even if it has free to play or does have early access, and this will influence their decision. Now, the cleaning I've done is I've dropped unnecessary columns from the original data. I've checked for missing values. I've dropped the records where the release date was missing. I've removed the day and year of the release date to only include the month. And I've removed the invalid month names from the release dates. I checked this by printing the unique release dates and seeing which makes sense or not. And I've also checked for outliers, but I've made no changes there. Now for the explanatory analysis. As you can see here, 1 in 5 video games don't have early access, and most games are released in August. Now, this is beneficial for CEOs who want to be different than their competitors. Maybe they want to release it in April, but you can see it's mostly equally distributed going down across the months. Other keynotes is a majority of video games are rated between 50 and 90. And most video games have a selling price of less than 50, which makes sense in the market today. Also, any video games can be released in any month and it will have a rating of 50 and up. And as you can see here, most games are priced below 50 and have a rating of 42 100. Most games don't have early access and don't offer free to play because, as in our data, I think early access only counts for about 5%, and no free to play only counts for about 10%. For feature engineering, I've dropped rows where the Metacritic score is 0. I've dropped the unnamed column 0. I've changed is early access from categorical to numerical. I've changed is free to play from categorical to numerical. And I've changed the months to numerical 1 to 12 rather than the string. And the order of importance when predicting the Metacritic score was the first one was price initial, which the correlation was 0.12, recommendation count 0.11, release month, no free to play, and no early access. This means that price initial, as the price goes up, the Metacritic score goes up, but the fact it's 0.12 means it has just a slight influence. And for the regression models, my highest model is model 4 with 33%, the R squared adjusted. And this meant that I explained 33% out of my whole initial total error. And the mean MAPE is 10.8%, which meant that when predicting the Metacritic score, we could be 10% above or below the actual Metacritic score. As you can see here in this model, where it's the error values of the actual Metacritic score versus predicted Metacritic score, we're nearly 10 Metacritic score above the actual value, where, yeah, and then in here, we're predicting the initial price against the actual Metacritic score. As you can see here, games below 5, we could be below -5 of the actual Metacritic score. and games around 10, we could be as high as 7 above the actual Metacritic score, or even minus 10 above the actual Metacritic score. And for the recommendation counts, above 50K is where our model suits best, because it's almost like a straight line where it's about 8 above. We're predicting 8 above the actual Metacritic score. And the fact that most games don't have free to play, and the games that have free to play, it only accounts for 0.05 of our data. We can ignore that, where we can't really say that's for definite. But anyway, for no free to play, we can be predicting 20 above the actual, or even minus 15 where it's distributed. My communication of findings is the model is, as I said, 10% below or above the actual Metacritic score. This is bad for highly rated games. Let's say the manager of Nintendo, if most of their games is 90 or above, then when he reports back to the CEO, it's gonna say 81, 80, 81. But that's not, and that's a big influence on his decision. The price and recommendation count correlation value of 0.12 against Metacritic. The higher the price or recommendation count, the higher the Metacritic score. But it's only a slight increase because of the small correlation value. The model is good for games that have more than 50K recommendation count. The predicted score is less than 7 above the actual score. So the more recommendation count, the less the error. The majority of video games recorded don't have early access, 90%, and don't have free to play, which is 95%. Now, most video game companies can use our model to see how their games are performing in the market, but they need to be aware that our model might be predicting 10 higher or lower than the true actual score of their game. There's a trend in the video game industry where most common price is below or around 50. And as a video gamer myself, I know that's true. And most don't offer free to play, which makes sense, and don't have early access. Also, there's no say which month favors a release date, as the month is the games are equally distributed along the months. The challenges I faced, well, in terms of code, data scraping was a bit difficult. I tried data scraping from Amazon and multiple pages, but at the end I couldn't get it, so I ended up using a CSV file. Deciding to drop outliers or not, the fact that I had 12K data, I didn't know whether to drop it or not. And getting the substring from the release date and dropping the invalid months took a bit of time. I had to search up on Google how to separate using white spaces. And the summary analysis from the graphs for the regression analysis took a bit of time. And in terms of theory, choosing suitable data set with good variables was difficult, because either they had too little data set or too much, or the variables didn't really make sense. Model 4 and 5 gave the same R-squared value, so I didn't really understand why it did that. I concluded that it did that because it's free to play and is early access was highly dependent together. So I ended up using Model 4 instead, and I left out his early access because his early access was Model 5. Understanding the highest predicted R-squared value was a bit difficult, but I went through this video, and around the 17-minute mark, it explained it quite well. And also the MAPE, I also went through the video and explained it good enough for me to understand. And in terms of the PowerPoint, I didn't know what was the difference between slide 6 and 7 and slide 8 to 9, where I thought that the model, where I wrote the model best suits games in the 6 and 7 was basically what 8 to 9 was. I ended up just using one slide instead of two for 8 and 9. And that's my CA. Thanks for listening.